We just learned that stereochemistry is the branch of science that has to do with the three-dimensional arrangement of atoms in molecules and compounds. Stereochemistry also has the presence of isomers in that discipline of science. Isomers is a concept that we already talked about, specifically in chapter 8. By definition, isomers are going to be two compounds with the same chemical formula that have different arrangement of atoms in a molecule, and it happens to be that that leads to different properties. So far, we have discussed constitutional isomers. And constitutional isomers are going to be two molecules that have the same chemical formula and they have the atoms attached in different ways. So that means that constitutional isomers are going to have overall different names. Also in chapter 8, we learned about cis and trans isomers. In cis and trans isomers, we observe that those molecules had the same chemical formula, but now we see that even though the cluster of atoms are arranged in the same way around the molecule relatively, spatially, there is a difference between the two molecules. That's why cis and trans isomers are known as stereoisomers. So let me repeat it for you. A stereoisomer is going to be when we have pairs of molecules that have the same chemical formula. They have the same cluster of atoms on the same molecule or on the molecules that we're talking about. But then spatially, those clusters of atoms are going to be different. So when we look closely at cis and trans isomer, for example, here we have cis-2-butene and trans-2-butene. We can see, and I'm just going to zoom in to look at this closely, that the molecule on the left, we have carbons that are double bonded to one another. The carbon on the left has a cluster of a carbon and three hydrogens, and is also attached to a hydrogen. The carbon on the right, meaning carbon 3, has a cluster of a carbon with three hydrogens, and it also has a hydrogen. Now, the clusters of the carbon with the three hydrogens are both pointing up. And if we look at trans-2-butene, we have the same arrangement of atoms in the same order, meaning carbon 2 still has a hydrogen and a cluster of a carbon and three hydrogens. Carbon 3 still has a carbon and a cluster of three hydrogens, along with a single hydrogen. So in terms of the atoms, we have the same clusters on both molecules. It's just that in the trans-2-butene, the cluster of carbons with three hydrogens are on opposite sides of that double bond. So that means that they are arranged spatially different, and that's why cis and trans isomers are known as stereoisomers. More specifically, trans and cis isomers are known as diastereomers. There is a different class of a stereoisomer. And that separate class of a stereoisomer is known as an enantiomer. Let's look at examples and different illustrations to understand better what enantiomers are. Enantiomers are going to be stereoisomers that are not superimposable mirror images of each other. If we look closely at our example, we can see in letter A at least the drawing in terms of their 3D structure of a carbon atom that is sitting in the middle of the molecule. And we can see that this carbon atom specifically has 1, 2, 3, 4 groups that are different from each other. And the molecule that we have on the right of that is just the mirror image. This is the mirror image of the molecule here. We can see it better illustrated in letter B. where we see the hydrogen facing each other, the chlorine pointing up. Behind the molecule, we have the fluorine, and then we have the bromine on the other side. Now, what happens in enantiomers is that those carbons that we see in these molecules, they need to be chiral. So if we look at the molecule on the left and the molecule on the right, these molecules are chiral. Now, I'm going to illustrate the whole idea of non-superimposable using the images from letter B. If you pick up specifically, okay, in this case, the molecule on the right, and you turn it 180, and then we see what the molecule looks like, we can observe that that molecule is not going to completely align with the molecule on the left, even though it has the same atoms, even though those atoms are arranged at least in the same order around the carbon. The thing is that these two molecules, because in terms of space, the atoms are arranged differently, the molecule on the right, even after you turn it 180, does not completely align with the molecule on the left. Actually, no amount of rotation can actually convert one enantiomer molecule into another. You may be wondering, why is stereochemistry so important? When it comes to stereochemistry, it is important to understand that stereoisomerism is extremely important in drug design, meaning in any pharmaceutical compound that it is utilized in order to treat a certain illness. So I want to actually give you an example of how, if scientists, or because scientists were not really paying attention to stereoisomers, they really affected a population of women and their children. I want to give you guys the example of thalidomide. Thalidomide is actually the compound that you see illustrated in the top of the right side of the slide. Thalidomide only has one chiral carbon, and that single chiral carbon is right here. Thalidomide was a drug that was invented at first in the late 1950s to help with morning sickness. And once it was synthesized, the two enantiomers of thalidomide were not separated when this specific medication was synthesized. They administered the thalidomide with both enantiomers of it. Then, after some time, when these women were having their children, they actually observed that women that took thalidomide for morning sickness actually delivered children that had physical disabilities. You can see, though, an example of these kids actually on the bottom right picture that we have on the slide. Additionally, it was reported that some of these babies born with disabilities had about a 60% fatality rate. And it was all because one of the enantiomers of thalidomide was actually helping with morning sickness, but the other enantiomer, which was present in the pill that was created, was the one causing the fatal effects and the creation of disabilities in these children. So understand that currently, when drugs or we call them drugs in general, but when medications are made, it is very important that when they are fully studied, that we understand what are the effects of individual enantiomers if the molecule that is created has them, in order to understand which one is the one that is going to help the illness versus which one may or may not affect the human body. So understand that it depends on the medication. Not all of them. One enantiomer cures and the other one is not curing or creating problems. But at times, this can be the case. Now we're going to proceed to look at ways in which additionally we actually write these molecules that are chiral. We learned a moment ago that whenever we have a chiral carbon, we can draw them with wedges and dashes to illustrate the 3D arrangement of those atoms. We can also utilize Fischer projections as a way to illustrate these molecules and understand that many carbohydrates are illustrated as Fischer projections. A Fischer projection is just a method to depict three-dimensional shapes of chiral molecules. We can see in figure 11.12 a ball and stick model for a monosaccharide that is called glyceraldehyde. And in glyceraldehyde, this part of the molecule is the aldehyde. And then we see a carbon atom that has, let me just zoom in. And I'm going to write in the atoms. It has a hydrogen. Let me write that this is carbon. And then that carbon atom is connected to a hydrogen, as I mentioned, and it's connected to an OH group. Is connected to a CH2 with the rest of the molecule, which that is a CH2 connected to OH. And then the upper part, this is a carbon connected to hydrogen. So the four different groups and the only chiral carbon in glyceraldehyde, we can actually see it right here because the groups are hydrogen, OH, this area of the molecule, and this area of the molecule. So that's why the asterisk is here because that's the only chiral carbon in glyceraldehyde. The molecule that we have on the right side is just the mirror image of glyceraldehyde. So this glyceraldehyde molecule, using my highlighter tool, I'm going to define how this is written in a Fischer projection form. We see, and I'm only going to do it with the molecule on the left. This is the CHO group. This OH group is here. This hydrogen is right here. This CH2OH is right here. And then the carbon that is chiral, meaning this one is not written and it is implied. It is right there in the middle at the cross between the two lines. So that is a Fischer projection. You can follow and try at home to do the same labeling for the molecule on the right. Whenever we have a Fischer projection we can actually look and define different isomer notations for them. In general, in carbohydrates and in other biomolecules, the DNL notation is what it is utilized to define what kind of stereoisomer we have for the molecule. Okay. So whenever we have carbohydrates and we're trying to define the D or L notation on it, what we need to do is find the chiral carbon that is the farthest away from the carbonyl group. Then you're going to look specifically in carbohydrates, where is the location of the OH in that molecule? So let's look at the compound that is called erythrose. Erythrose is a monosaccharide, and the chiral carbon that is the farthest away from the carbonyl, I'm just going to circle it, is this one. Then that chiral carbon, which is the farthest away from the carbonyl, since I have my OH pointing to the left, then that is the L version of erythrose. Now, if I'm trying to see what is going to be the enantiomer of that molecule, then what I'm going to write is the mirror image of L-erythrose. So we can see here that this molecule that you see written on the right, it is the mirror image of L-erythrose. And we can see that because the H's are pointing to each other, the OHs are pointing towards the back, and now we have specifically the aldehyde motifs there and the CH2OH right there. So if I look at the mirror image of L-erythrose, I see that if I look again at that molecule, specifically at the chiral carbon that is the farthest away from the carbonyl, and you can see that I actually marked it. Now my OH is pointing to the right. I always say that right in Spanish is the word derecha, which starts with the letter D. So if your OH is pointing towards the right, meaning derecha, that means that that is the D isomer. The image that you see below of Samuel L. Jackson is just a funny meme that I found in which it is illustrating that if something is looking towards the left, like this image, that is the L isomer. But if Samuel Jackson was pointing or looking towards the right, then it should have been labeled Samuel D. Jackson. So it's just a funny meme to reiterate the DNL notations that can be found in carbohydrates.